Hi, my dear students, how are you? Welcome to a new lab session 5, dealing with interrupts. Now, interrupts is a very interesting topic, and I'm very excited to show you the power of interrupts. Let me tell you just one thing that interrupts, although it is very amazing, but it is very less understood by people in general. Particularly in academia, the students they try to bypass the interrupts, but as we see in this lab session, you'll see the power of the interrupts. And I've taken a detour from the normal 8086 architecture, so many of you will be interested in knowing that as well. So let's begin with the interesting transition. All right. So what are interrupts in microcontrollers? So I'll read this out. Hear me carefully. I've tried to write exactly what I wanted to speak. Interrupts in 8086 architecture or any other architecture refers to signals that interrupt the normal program execution of the processor and cause it to temporarily stop executing its current instructions to handle a specific event or condition. So you can see that in this diagram, if certain operation was happening, then if an interrupt occurs, then it moves on to a different execution state, the microcontroller. And this is how just a diagram to help you visualize how the flows is happening, and then again it comes back to its original execution state. All right, and these external events can be generated from anywhere, like your keyboard, your mouse, timer, external infrared remotes, or anything. And it can also be software based internal conditions such as errors or exceptions. All right. So the 8086 microprocessor has two types of interrupts in general. If, like most any architecture has two interrupts: hardware interrupts and software interrupts. I've written particularly 8086 just to tell you that first of all, this is a chip of 8086, a packaging, a dual inline packaging, and some of these pins you can see are we do not know as of now. You'll see it in future lectures about what each of these pin does, right? So hardware interrupts are like externally applied interrupts, and they put a high signal onto one of the particular pins, and then to tell which interrupt is being raised, they apply certain address to the interrupt lines. More on this in later sessions. As of now, in this lab session, we are more interested into software interrupts, also known as system calls, and are generated by software programs to request the operating system to perform a specific operation or service. So software interrupts are triggered by executing a specific software instruction called the INT instruction. Very important, INT instruction. Here we'll be using a very specific version of INT instruction for 8086 architecture. So stay tuned. Okay. So what are interrupts in microcontrollers? Finally, in summary, interrupts in 8086 architecture allow the processor to handle external events and internal conditions in a timely and efficient manner without requiring the program to constantly keep checking for them. So I have a very good example to show you. Let's look at a practical example of why interrupts are important. So I have designed this, you can see it right here. And I've already pre-recorded it because it was a little difficult to show on the webcam. So I've recorded this, and we'll see basically the what I'm trying to do is here I'm handling the normal routine procedure of the microcontroller which it has to handle. Like I'm just measuring the distance of an object from the ultrasonic sensor and trying to figure out and map it to the LEDs. Basically, the more closer we are, the more LEDs will blink, indicating a danger. And then I have a button here. Like if I press this button, it basically means that an interrupt is raised, like a crash has happened or something has happened, and all the LEDs have to be lit up immediately, no matter like what the ultrasonic sensor is reading. Okay, so let's see this in action. Try to observe how the hardware performs, and I'll show you the code first of which I wrote in Arduino. So this is the Arduino code, which is without the model, without the interrupt. So I'll let me just give you a very small explanation of the code. That here these two trigger and the echo pins are for initializing the ultrasonic sensor for sending a trigger and receiving the echo. And we have the LED pins here defined with this. Then we have the duration and distance, two variables just to help us map whatever we read. Like I won't go into the depths of the code, and there's not even required. I think easily, y- by second year, many of us have already interacted with Arduino or we have heard of it. but I would highly recommend those who haven't interacted with Arduino. It's a very good tool to, actually, it's like a, it should be in our back pocket always, just like our wallet. So although I'm not a huge fan of Arduino, but I'm seeing in general some microcontroller. All right. So the pin modes are defined here. I'm defining all these LEDs as output, and I'm taking the button as an input. Okay, so your focus should be on the button only as of now. So what is in a general execution of a program, like if I have to, indicate that thing like button press. So first thing which I'm indicating is button press. So digital read on button. So if it is button is pressed, then A will store a high value like 1, or else it will store a 0. So if that is the case, then these all the LED pins will be set to high, and if it is like, not set, then it will just skip these lines of code, and then based on the distance which I'm calculating using the ultrasonic, I've calibrated, and then I've mentioned the value 17, 20, 25. So this is after calibration, if you're wondering where these values came from. Based on that, I'm lighting up my LEDs. Okay, so let's have a performance check. All right, I'll play the video. So this is a remote which I'm bringing close. Now observe the LEDs. So system is not very responsive, and now after 2 clicks, so many clicks, oops, doesn't look good, right? So what just happened here? Try to analyze what just happened here. So clearly the system is very laggy, and the most important thing, the button press is an unexpected event, and our code is clearly not ready to handle that unexpected event. So if you notice that, I'll just open the code once. We might be, we might be at this stage of execution somewhere we are, checking one of these if else conditions and doing some calculations, and that is the time when we press the button. But our code is not ready to, do the digital read, or that transition of the button. It's not ready to, only when it is at this point, at the starting of this point, since it's a loop, so it goes in a round robin fashion, like it always comes back after the end, it goes back to the top. All right, so only when it is at this, like at this instant, will it be able to detect my key press. So isn't this like too weird? And that is where the power of interrupts come. All right, so therefore it has to be modeled as an interrupt, and what we do next is button press captured as an interrupt. So the code will look very similar, but there are a few more variables which we have here. So I've defined a button state, which you'll see the use of the button state. The most important line is this attach interrupt. So whatever my pin mode for the button pin was, I have attached that interrupt, that same button pin, to the digital pin to interrupt. There are two interrupt pins on Arduino, pin 1 and pin 2. Therefore I'm using pin 2 as my button pin. If you're not understanding that, it's completely fine. Like you don't need to go and I'm just showing you a very practical example, and those who are already interested, they might be, enjoying this, seeing this code. So if I'm attaching an interrupt, so now it will go to blink 1, and what I'm doing is I'm catching the falling edge, like when the button is pressed, that is the falling edge, so I'm just trying to capture that. Okay, and if the interrupt occurs, I'll just go to my execution to the blink one, which I'm defining to the later half of the code, which is this. I'm printing, many times high, like H double I. So just, please do something. Interrupt is raised, do it quickly. And what I'm doing exactly is button state is equal to not equal to button state. Just to show you, like I have modeled it this way, like I've just changing the button state. There can be n number of possibilities, better methods which you can use for writing in your interrupt service routine. Now this is known as ISR, interrupt service routine. After this has occurred, wherever the program was, when it, when that interrupt had occurred, exactly to that point will, it go. So this is not the 100% right way of executing things, but just to make it very clear and to capture all these things in a video, uh, I have done it this way. So if it was anywhere outside executing these lines of code, wherever we are doing the digital, that ultrasonic reading, if I press a button, it will go inside this and will change the button state to not equal to button state and will come out. And the next time when the loop happens, it will enter the button state. Like since it was originally false, so it was executing its normal routine procedure, But as soon as interrupt was, I'll raise the interrupt by pressing the button, it will go inside this and will set all the LEDs to high. All right, so let's see it in action. And this is not 100% right, so you might see a few mistakes here, and this is up to you, and you can even, feel free to come and discuss with me. I'll be more than happy. um, like, this is not the 100% way of correct way of coding it. It's just like my first attempt, but of modeling interrupts, just to explain you all. But after that, I realized, after shooting the video and everything, that I could have modeled it in a better way, in a much more efficient way. So now it's up to you. Like, you can also do it at your end, and can feel free to come and discuss if you feel anything. All right, so let's see the video now. By the way, the disturbance which you're hearing is of ultrasonic sensor. So see how responsive the system is, first of all, how responsive it is. And see, just see how, you know how quickly we're able to map this. So we're able to capture the interrupts, and that is the best part, right? And what did you observe now? Just think about it. We have certainly a faster response time. We have reduced CPU load. So pause the video and read through this, that what I've mentioned here. It's important that you get an correct understanding that the first thing is very important. Actually, few of these things are important, so I'll read them. Interrupts allow the microcontroller to respond to external events almost instantaneously as they occur. And this is because the microcontroller can suspend the current task which is it is executing and immediately jump to ISR. So that hi which I had written, and changing the button state, it will immediately execute that as soon as I press the button. And I'm also capturing this on the serial monitor. You can see, like, this is my serial monitor here, and I was able to, like, as soon as I press the button, it was coming, and with coming without a fail every time, every single time I pressed to do this experiment. But LED logic, changing logic, I've not modeled it properly, that I've told. So one button miss, you might have observed in the video, and there is a perfect reasoning to that. But interrupt in general has not failed. Every time I press the button, the interrupt was raised, and I could see it in the serial monitor. And let me just tell you very quickly, since I have since already raised that point. What if I'm already inside this while loop when the interrupt when the interrupt is raised? So think about that. I've not modeled it perfectly, so that is why you might have seen some glitches in the video. All right, so reduced CPU load. In contrast to interrupts, there is the polling thing, right? So polling is like, you keep on asking, आया क्या button दबाया क्या दबाया like, did someone press the button? So it's like too much unnecessary load on the CPU, whereas it could, simply, if it has nothing to do, it could go to a sleep mode or something, which is like the last point, energy efficiency. And as soon as something comes, an interrupt is also raised along with that, and then it rises, handles the interrupt, again goes back to sleep. Energy efficiency, Internet of Things, IoT, that is all about it. So simpler code. Interrupts can simplify the code by allowing the programmer to write more modular and reusable code, right? You can see the complexity of, previous thing versus this interrupt thing. It was so much easy to write, handle the interrupt service. Whatever I wanted to do as an ISR, I could have simply brought it down to the interrupt service routine. And in fact, it is interrupts can be used to raise precise timing in real-time operating systems, in real-time applications, which is, I won't discuss it much because it's another very big topic, and it's very, like, not in the scope of the discussion currently. So now let's understand interrupts theoretically with Dr. Vinay Chamola. He has recorded a lecture for us, so let's view that.
So welcome students. In this session, we'll be looking at the software interrupts. So as all of you must be knowing, right, we have this particular system hardware, right? Over the system hardware, you have basically BIOS, and over that you have DOS or your particular operating system, and over the operating system you actually have application programs or certain commands which you can actually run. So you see that in this particular thing, between the hardware and the actual applications which you are running, you have the BIOS and the MS-DOS, right? So BIOS, if you actually talk about BIOS has a very important role, as we had discussed in the very beginning of the lectures on this course also. So now the BIOS is basically hardware specific. It's basically provided by the manufacturer. It has two parts. It has the resident BIOS and the non-resident BIOS. So resident BIOS can't change it. It's within the BIOS, right? And the non-resident BIOS, it basically offers convenient ways to add several functionalities into BIOS so that later on, say you want to change something and so on, you can actually change. The BIOS can be used for testing and initializing the input I/O devices. Also, it's also used for loading the bootstrap loader. Basically, when you have to right kind of load the operating system and so on, because your operating system, at as we had actually discussed earlier, operating system generally lying in the memory, right? The secondary memory. So if something is in the secondary memory, the microprocessor or the processor can't access it. So that has to be actually brought to the primary memory, and this particular task is done by BIOS. So BIOS actually is lower layer than the operating system, and right, even the BIOS you can actually kind of make many kind of a changes and so on. So if you kind of press the F5 button and so on, at times you can actually get the user interface where you can actually use BIOS for doing configuring various kind of things and so on and so forth, kind of controlling input output devices, right? And when the system starts, it does various kind of things, right? It kind of checks the, basically it tests the input IO devices, right? Kind of checks the memory and loads operating system and so on and so forth. Now, here from after this, we come to an important junction where we actually kind of look into what interrupts are. Interrupt, basically, whenever you have a microprocessor, what does a microprocessor do? Right, you have certain set of commands, you have set of instructions, and it is actually executing it in a particular flow, right? Now, when there are few instructions which are being executed and you want to change the flow, that means you are doing this thing, and say you want to kind of jump to certain other kind of instructions which you are executing. Can do it in various ways. Can you use call, and you can write either use a procedure, you can use macro and so on, and you can actually move the control of the program from this csip or this particular code location to another location. There is another way also to kind of change that flow of right operation, which is basically called as interrupt. Even in common English language, right, when we say interrupt, what does it mean? Something normal is going on, you suddenly interrupt the person and kind of right ask him something or ask him to do something and so on, right? And here exactly we have a similar kind of thing. So interrupt, what it does is it breaks the normal execution of the lines of the microprocessor, and it does certain kind of thing. Now what kind of thing it does? So generally you have a vector number basically which tells what kind of interrupt it is. So you have a 8-bit, right, 1 byte kind of size of interrupt vector numbers is called vector number. And here we'll be looking at two major kind of interrupts, which are the DOS interrupt and the BIOS interrupt. So now the DOS interrupt and BIOS interrupt, they have the vector number 21 and 10. So the DOS interrupt has the vector number 21. So as soon as you say in 21, that means that I'm going to use a DOS interrupt. As soon as I say in 10H, it means I'm going to use a BIOS interrupt. So now interrupt, it operates very similar to call. That means it's kind of switching the flow of operations or instructions to some other place, right? So at that particular time, you may have certain flags, you may have certain. So this is where I am, say, before the interrupt being called. So I have a particular CSIP which is actually pointing towards the next instruction. As soon as I get into this interrupt, the CSIP and so on and so forth, all of these may get changed. The flag registers may get changed. So what I need to do, right, before this interrupt or as this interrupt gets executed, right, my first step will be what I will push the flag to the stack, right? of course, this TF, the trace flag and interrupt flag will be cleared because they will be changed in the interrupt execution. Then I push the CS content, I push the IP content to the stack. So what I have done, the flags, the CS, the IP. So I have pushed this to the stack so that later I can sort of retrieve it. When I push it, it will be sort of like this. The flag, right? Then the CS, then IP. So if you remember the stack discussion, later when I kind of do the pop, I have to pop this first, then I have to pop this, then I have to pop the flag, right? So now by pushing this particular values, of course, this happens automatically. When before calling the interrupt, you don't need to manually write push flag, push CS, push IP, and so on. As a course of the instruction, internally the microprocessor pushes these particular register, the flag registers and so on. Let's see this particular simple example. Here, just imagine that you had interrupt 08H which was executing, and you had the current content of CSIP and flag value as this particular value. So what happens? Assuming that the stack pointer is initially at 0050H, what will actually happen is the stack pointer will be decremented by 2, right? Decremented by 2, and what will be stored first, right? The flag value will be stored first, and again we'll follow the little Indian: lower memory location, the lower bits; higher memory location, higher bits. Then after that, what I am going to store? I am going to store the CS, then I am going to store the IP, right? So you had the flag, CS, and IP. Simply just put on the stack, fine. Now one will ask that, okay, you told that, okay, these CS and IP values are preserved. That I understand. But once this particular interrupt is called, where is my program going to jump? Right? At what CS, what IP, what location will it actually jump and start performing the execution? So the method for that is that the vector number. So like here in this case, we had int 08h, so the vector number is 08. That is multiplied by 4. You get, right, value 32, which is 20h. Then what it does, it will go to interrupt service routine. About, don't worry too much about this. Later when we'll have discussion on interrupt, we'll discuss in detail what is this interrupt service routine table, how it is populated, and so on. Just simply understand that it will basically go to this ISR table, and it will go to this entry. Because this was 20, it will go to 0020h, and it will read these particular values, right? So what it will do, the first two memory locations, it will get the IP. Here it will get the CS. So as you see over here, the CS value this, IP value this. So from this, basically, it comes to know where it will, right, kind of go for executing those particular operations. Now, once your interrupt gets executed, in the end of the interrupt service routine, you have the IRET. So IRET, what it does is, right, as I had discussed earlier, before the interrupt actually executed internally, what it did, it pushed the flag, pushed the CS, pushed the IP. So later when the IRET happens, what will happen? It will pop the IP, it will pop the CS, it will pop the flag, right? So there's just a kind of discussion I took, right? So these values will be popped one by one, right? This will be popped and so on and so forth, right? This discussion I just gave so that you have some basic idea of how the interrupt is working. More details, of course, we'll see later on. So now coming to this particular exercise, which you will be actually looking in this particular lab, we'll be discussing few DOS interrupts. Just like if say you want to read a key pressed, whatever key you have pressed. So of course this interrupt can is used, but in addition to that, right, using this int21 or DOS interrupt, you can do a plethora of kind of things. For example, you can in the DOS interrupt based on what value you are loading into AH, right? So AH gives a means of telling what DOS operation you want to perform. Depending on what value you actually load in this value of AH, when you call int21h, that thing will happen. For example, if you want to read characters, right, from the input terminal and so on, you need to put 0 1 value into the EH. Similarly, if you see something like if you want to read a buffered input, right, you want the kind of user to kind of give input on the terminal and you want to read it and all, you want to take a buffered input through it, you can give 0 right? Similarly, console input, then you have many other kind of commands. So I have added a sheet which gives details of each one of these. And of course, in this particular session, we will be just looking on into simple kind of instructions or DOS operations, not very complex like file opening and all. That we'll be seeing later on. So let's look at few simple examples. So the first example is you input a character from keyboard with echo. So now this particular kind of thing, if you see, input a character with echo. So now the code for that is move, of course, in 21h. In 21h is there for all DOS kind of right kind of interrupt. What particular thing you want to get do, right, that you mention by putting value into EH, right? So you put 0 1 into EH. What this will do is it will copy this particular whatever you put in the terminal or the program, right? It will store that value which you have typed into AL, right? And it will echo also, it will kind of display that on your screen also. Now, input a character from keyboard without echo. You want that, okay, whatever character you are putting, A, B, C, or whatever kind of thing you are putting, that should get copied into, right, string, whatever. You want it to get copied into AL, but you don't want it to, when you have your DOS box and you have open, you don't want it to get displayed and all. So you have 0 8, right, character read from stdin, no echo. It won't echo, it won't kind of display on the screen. Now here I have another example. Input a string from keyboard. You want that, okay, just not one character, but I want to take input from the user and he can add kind of input a whole string. So here we need to, of course, kind of, because string can be of unlimited, whatever kind of size and so on and so forth. We want to say limit it to 32. That say we want that the user can actually give us kind of an input, but it's maximum 32. Now this 32 is actually including the enter key also, because in the DOS box or your terminal, when you are actually typing whatever the string, in the end you press enter key, right? So it is having one extra thing that right, the 30-second is for enter key. So here you can actually put 31 characters technically, right? And after that you have one particular byte location left. So this particular thing, what it does is act 1, this is actual count of key that the user types will be stored here after int has been executed. So this is how, when you are kind of reading the string and all this particular through this particular command, what happens is this particular location, okay, it will come to know that how many characters are allowed, and in the immediate next location it will kind of store, right, how many you actually entered. Like for my case, like say if I enter Vinay 1 2 3 4 5, it has 5, right? So after this program is executed, the whole program of kind of reading the string and all is the storing the string is executed. What will be stored in act 1, right? 5 will be stored. Why? Because the name I entered here is Vinay, and I can up to maximum 31 characters I can put, and then of course one I have reserved for enter key. Then you have LEA DX max 1. So this is how right, if you go into details of this, the buffered input, how it works, right? So this is how it does. You have LEA max 1. So what it does is it basically kind of copies the this particular location, dx into dx. Then what you do, move ah 0 what it is indicating, 0 is basically indicating buffered input. That means the user can actually send the input. So, and then of course you have the interrupt which is happening. So after this particular thing happening, act 1 will contain the number of characters which are read, and the characters themselves will basically start at input 1, right? That's why you kind of stored for this. So this particular interrupt, when used along with 0a, works in this particular way. It looks for dx to see how many maximum kind of characters are allowed, and it kind of, after the whole execution, in the next memory location it stores how many the user actually entered. And one location after that, right, you will have whatever string the user actually entered. Like in my case, if I entered this thing, it will be stored from here, right, in the memory location. So later you can go in memory location and you can check the content here, here, and of course here you have put the value, right? So the characters will be terminated by carriage return, although this will not be included in the count and so on. So of course, as you do the lab exercise, you will see more details. So now this one is another thing, which is the purpose is to output a character to the display or STD out. You want it to be displayed on the screen. So what you do is move DLA. So that when we are using this particular kind of functionality, that means 02. If you carefully look at 02, what does it say? Write character to STD out. So whatever character you have given, so if you go into details of how this particular thing works, it works in a way that you have to put that particular character into DL, and when you execute this particular command, right, whatever is stored in DL will be actually displayed on the screen, right? Then you have this another thing, std out, right? This particular command, as you see, what it uses is 09h, moves into ah. So if you actually look at this 09, what does it say? Write string to std out. So this is what you want over here. You want to output a string on display. So you have this string 1 and you want to get it displayed. Of course, strings we generally terminate with this dollar sign. So it's a common practice. It's a good practice to terminate all strings with the dollar sign. So here what we did was load effective address dx string 1. Right. So this particular, whenever we are using move eh09h, of course, these kind of things we don't expect you to mug up, right? That's why we have these things in the lab exercise, right? And you can always refer to how these particular instructions are actually working and all. So what we did was, so what this particular kind of thing does is, it actually, when you load 09 into eh and you kind of run this interrupt, it's actually going to display the string on the std out. But which string? Which is actually pointed by dx, this particular thing. Fine. So it actually goes to dx. So now dx is actually kind of pointing. You did lea dx string 1, so it is basically pointing over here, and it will actually later on, what this particular thing will do, it will actually execute, it will display hello, right? You can of course remove this dollar sign and you can just check out in the lab, right, what happens when this thing happens. So I think this gave a kind of brief orientation you on today's session, and right, and best of luck. And there are of course two tasks. So the first task is straightforward. You need to write a ALP that takes a string of maximum 20 characters from user and displays it on the next line of the screen. So this is the one which you will be doing in the one lab, and then in the another lab you will be doing task 2, which is a bit more complex, which actually requires you to display the string and so on and so forth. Right. So here what you want is that a string of maximum 20 characters, you want to take it from the user and you need to display it right on the next line. How you can do on the next line? Of course, here we have explained that right the ASCII equivalent of the new line is 0dh, which is enter, followed by 0ah, which is next line, right? So please try to solve these particular problems. If you have any queries and all, right, our team of TAs, instructors, and all of us are there to help you. You can post your queries on Slack. Thank you very much.
All right, so here we are back again with a follow along example. So let me change to pointer and open the DOS box. So I was already working on this. Let me quit it. So I hope you guys are expert in mounting now. Okay. And one thing which I wanted to tell, I'll show in the flow of the code only. So here is our week 5. The first thing which we want to test is input a character from the keyboard standard in with echo. There is another command without echo, which you can see. All right. So this is all there in your lab manual. Just refer to that. We'll execute something here. So let's open the debugx and I'll show you first demonstration of how to input a character. So int 21 now you already know about it, right? So let me just simply go ahead and execute things. So I'll go to the assembler command and first thing which I'll do is move ah01. All right, sorry, something had to be addressed. Therefore, I had to pause the video. Anyways, so here we are, move age 01, and now I'll type int 21. All right, so these are the two commands which I want to execute. I'll go to my unassembler view and look at these two commands. All right, if I check my instruction, which will be loaded next is move age 01. So let me execute that using the T command, and age is loaded with 01. And now if I again press the T, it's asking me for a prompt. All right, so let me type in A. So you can see that A got printed, and just after that, these registers got printed. So it's a little confusing, and we'll see, like, throughout the sessions, you'll be working on how to make it more aesthetic, aesthetical, is that a word? Basically, make it look more pretty. And all right, let's try out the second command, which is without echo. All right, so I think that you can do that easily. Let's skip that. Now comes the interesting part of input a string from a keyboard. All right, by the way, one thing important to notice in this is that AX actually stores the AL is storing 61, which is the ASCII of whatever I've inputted, right? So if I take my instruction pointer back, let me do it by RIP, and let me take it back to the point um 0102. All right, so the obviously the next instruction would be again raising that interrupt. So I'll raise the interrupt, and if I type, let's say, uh, any, so you can see that the ASCII of that is stored here in 2A, whatever it is. Like it, you can just verify, like, things. I I'm guessing star is 2A only. All right, so whatever value you put, that gets stored in the AL. That is one thing important. All right, and do not fiddle with the AH, because AH is what is dictating the int 21 to what to do. All right, so do not fiddle with that. Do not change 01 just for making things look easier for yourself. like 2a के आगे 00 होना चाहिए, so just let it be there. All right, it's important. Now input a string from a keyboard. So I've already coded this, and here is the code. So it's very simple. Let's just quickly understand it. And we have dot model tiny dot 486. No need to mention this, but okay, since it's there, I've kept it. Max db. Now all these things are very important for you to actually understand that these are stored in sequentially in the memory. These are stored sequentially in the memory, all these things which you're seeing here, right? So first thing, i'll I'll comment out all these things, and the first thing which we'll do is just observe how the memory locations are. All right, so max refers to what are the maximum number of characters which are allowed to be inputted when I'm inputting a string. Act 1 stores the number of the count of the characters which has been inputted by the user, and what was the string which has been input is stored in input 1. All right, so let's first of all try to see this in action, this much part. All right, so ml and week 5 underscore c1 dot asm. Now anytime you're numbering your giving a name to your .asm code, it should not be more than 8 characters. All right, so right now I'm using 5 6 7, exactly 8. So let's load it in debugx and see debugx week 5 underscore c1 dot com, unassemble it, and no, like there is no instruction in the .co .startup, so nothing of that value. But we want to acha, we have to load at least one of this so that we can go to those memory locations and see. So let's quit it, and so 0108. So D0108. All right, so you see 32 in hex is 20, so it is coming here. After that, Act 1, there's a space for that. And then there are 32 locations after this where we will store our input, whatever the user inputs. All right, so let's go ahead and raise this interrupt and try to see this in action. Quitting it. So this time I have to look at the location 010C. Remember that. Okay, I might forget 010C. So 20 and 01 at 010C. What I need to observe is that if I enter in a string, the count of that string should come here, and that string in itself should start appearing from here. You can see the ASCII corresponding ASCII characters here and the hex values here. So let me do that. Trace command, and now I've raised the interrupt. So it's asking me for a prompt. So as always, I have a habit of writing many. Okay, so how many characters I have put? Just count 14. Anubhav Elhens 14, right? So what should go in my after 20 should what should go in 0A. So let's see if it comes. All right, D010C. All right, so I have 0E coming here, which makes sense, right? The Act 1 is storing whatever the Act 1 is pointing to. Uh, that is storing the count, and all my ASCII characters are coming here after this, up till this point, unbalance 65, and then this character is also there 0D. So you might have already read about this in your attend the lectures. Do not miss the lectures. I cannot compensate everything in the lab sessions. Like even I don't want to compensate, just like this practical session, all the theoretical understanding you need to get from the lectures. It's important that you attend the lectures. All right, so let's go back to the slides. So this we have just now covered. So after the interrupt one, act one will contain the number of characters read, and the characters themselves will start at input one. The characters will be terminated by the carriage return ASCII code 0DH, although this will not be included in the count. There is an important note. It's very important for your exams perspective. So just scaring you. I don't know. I'm not setting the paper or anything. So output a string from keyboard. So let's try this out. Or like this is very simple, straightforward, that you have a string, you just need to end it with dollar. And now if you load in dx the starting address of your the base pointer of this array of this string, and in move you move 09 into h, and then you raise the interrupt, then you can see that string appearing there. All right. So remove the dollar sign and see what happens. So next you have to do attempt your lab tasks. Lab tasks we are keeping a little easy so that it's a new topic to digest and you haven't got over from the previous topics. Let me tell you one thing, palindrome is a super easy problem. It's very simple. Like to have, is this pen working here? So I'll just explain that if you are standing here, like this is, let's say this is you and this is your friend, and you want to come one step closer here and he wants to come one step closer here, but then a person is there who pushes both of you in this direction, like a wind or something, like so you reach to the correct spot now. All right, you reach to the correct spot, but your friend, instead of coming one step backward, he reaches one step forward. So now what? He simply has to decrement two steps. So if this was your si and this was your di, and by comparing using the compare cmpsb, comparing your strings, si and di, both si and di got pushed further. So si has now reached the correct location, di has reached one step forward, so all you have to do is decrement di two times. So this is the trick for handling the palindrome problem. All right. uh, Very easy. Okay. So anyways, attempt your lab sessions, and that is it. Thank you so much.